So now we introduce triple product. So now we have three vectors, and we want to multiply them together. So the first one I'm going to introduce is scalar triple product, which means you have three vectors. After some kind of multiplication, you end up with a scalar. Now, what choices do we have? Well, we have three vectors, A, B, C. A dot B cross C. The third one is A cross B cross C. Right? We only learned dot product and cross product up to now. So now you have three vectors. You want to multiply them together. So what choices do you have? You can have two dots, one dot, or no dot product. Right? So these are the choices you have. This is really a test to your understanding up to now. A dot B results in a scalar or vector. TA. What's the result of A dot B? Scalar or vector? Scalar. Very good. Yeah, scalar. Okay? So A dot B is a scalar. Scalar multiplied with a vector gives you a vector. Okay? My target now is after triple product, I need to have a scalar quantity. So the first choice cannot give me a scalar result. Second one, B cross C is a, call it D, scalar, right? Vector. B cross C gives me a vector. So I now have a vector making a dot product with another vector gives me scalar. So this is yes. Okay. Third choice, three different vectors making direct cross products. A, B gives me D, so D cross C gives me E, right? So the third choice cannot give me a scalar. So when you have three vectors making multiplication and you want to arrive at a scalar, this is probably the best choice, right? Probably the only choice you have. So what's the physical meaning? A dot B cross C or B dot C cross A, whatever, you have three choices, right? You have three different vectors, A, B, C, and somehow you want to perform multiplication and arrive at a scalar. What's the physical meaning of that scalar? Yeah, I'm showing you again and again how nice I am. Read the first sentence. If you have three vectors in space, they encompass a solid volume. So this is the proper way to find that volume, 体积, encompassed by the three vectors. Why? For example, we look at this one, A dot B cross C. So B cross C, if you remember, is the area with certain direction, right? It's basically a surface. And now you make the dot product of A to this B cross C, you're calculating the volume. And volume, 体积, is a scalar. So the physical meaning of cross product is to find the surface encompassed by two vectors. And then you project onto a third vector, you find the volume. So this is really giving you the physical meanings of dot product, projection, cross product, finding the surface, scalar, triple product, finding the volume. Right? Now, we have another triple product. which is vector. And this one you're not very familiar, but A cross B cross C. So this is again called Lagrange formula, but usually we don't like to perform cross products in the calculations. So I'm trying to teach you, and later on you will use it. So I'm providing this for you as a tool. So the scalar triple product, the vector triple product, A cross B cross C, can be simplified into dot products. Okay? So the trick is A cross B cross C is equal to back, your back, minus the taxi, cab. Okay? In the United States, taxi are usually called cabs. Cab, C-A-B. Okay? Back, B-A-C-K, you drop the K, right? So back minus cab. But if you look at it, B vector is now multiplied by A dot C. A dot C is a what kind of quantity? Scalar or vector? Scalar. Easy to calculate. So for example, this is maybe 5. Right? 5 times B minus C multiplied by A dot B. Again, a scalar quantity, maybe 2. Right? So we're trying to simplify complicated vector multiplication into easier dot product, scalar multiplication. Okay? Remember, A cross B cross C equals to back minus cab. So the orders are very important. A, B, C, you have to write it B, A, C minus C, A, B. Back minus cab. Okay? So if you want to read the proofs, you can do that in the textbook. Example 2-3, there's a detailed proof. But what you have to remember is back minus cab. Okay? This will be used in our later derivations, especially for magnetic fields. Okay? Alright. So I still have 10, 11 minutes. And I assume there's no question because up to now what I covered are very fundamental. So I want to move into orthogonal coordinates. And I will introduce 3 types of them. But due to time limitation, I might be introducing Cartesian and cylindrical for today. Before I really introduce Cartesian coordinate, I want to introduce one simple knowledge, okay, to all orthogonal coordinate. Oh, by the way, I asked you what this orthogonal stands for. Do you have any answer? Orthogonal coordinates are here to help us to simplify our calculations. Alright? But it's based on our understanding to dot product and cross product. So that's why I spent so much effort in introducing dot product and cross product. Is there any answer from the student? Orthogonal coordinate. Meaning, we live in a 3-dimensional world, so we need to have 3 unit vectors. For all the coordinate systems, we want to define using 3 different unit vectors. And usually for simplicity, we want to have the 3 unit vectors being perpendicular to each other. Okay, so this is like my hand. Each 2 are orthogonal. Orthogonal means perpendicular. Okay? So we will have 3 mutually perpendicular unit vectors to define as a coordinate system. Therefore, each two are being perpendicular, so this is what you should apply what you just learned to the definition. A unit vector, first one, second one, right? I and j can be 1, 2, 3, 2, 3, 1, 3, 1, 2. For example, A1 cross A2 should be A3, right? So this is the definition of orthogonal coordinate. This is 1, and this is 2, and they are perpendicular. So 1 cross 2 equals 3. So they are all perpendicular to each other. Okay. That's the first sentence. Okay. Written in math. And this relies on your knowledge to cross product. After you perform cross product, the result is perpendicular to both. Okay. Then we need to add another constraint to satisfy and guarantee each two of them are perpendicular. Because the first one only tells you this one, the third guy, is perpendicular to the second one and also perpendicular to the first one, but there's no guarantee the first one and the second one are also perpendicular, right, up to now. So we need to ensure that here. So any two unit vector making a dot product, making the projection, will be 0 when your subscript are different. For example, 1.2 should be 0, but 1.1 equals to 1, right? So using these two simultaneous conditions, we ensure the three unit vectors are perpendicular to each other. Okay? So the choices, well, you can have x, y, z, Cartesian, cylindrical chord, or spherical, but let me just try to emphasize what are the benefits for introducing orthogonal coordinates. So let's take a look. I have two vectors, vector A and vector B. Each vector can be expressed in any orthogonal coordinate system. Okay? So you have three components, each telling you its magnitude in what direction. Okay? So A and B are both now expressed in some form within some orthogonal coordinate system. So what are the benefits? What if I ask you to perform dot product? Without drawing the vectors, once you can write the vectors in that given orthogonal coordinate system, you can perform immediate and direct calculations because A dot B, by definition, each vector can be written in three components with their corresponding directions, right? Unit vector 1 with that length, unit vector 2 with that length, unit vector 3 with that length, so on for B. So you have three components multiplied by three components. So ideally, you would have 9 terms, right? So you would have 9 terms. How can that be simplifying our process? But the truth is, with our knowledge to orthogonal coordinate system, within the 9 terms, you only care about 3 terms. Do you still remember why? Because I'm showing you the 9 terms, but eventually, all the cross terms, for example, A1 times B2, like the first term multiplied by this term, would vanish because, due to the fact, orthogonal coordinate system tells you the unit vectors are inter-perpendicular, right? Inter-orthogonal. So A1 times unit vector A2, that term vanishes. they don't have projections. They are perpendicular. So eventually, all you have to collect are the terms with identical unit vectors, right? A1, B1, A2, B2, A3, B3. So that's what you have. So you don't even need to draw out the vectors A and B, right? In the past, in high school, whenever you're given two vectors, you need to calculate their length or magnitude. You also need to know their angle. But now you don't, right? You don't really need to draw these two vectors out. You can just do direct calculation based on the knowledge of orthogonal coordinate systems are having three unit vectors and they are perpendicular to each other. So a more fancy way of writing A dot B in using orthogonal coordinate is like A times B. Use a matrix form. Okay. Then you have A1 B1 plus A2 B2 plus A3 B3. Let me show you the next example. Cross product. Usually people hate cross products. Again, two vectors A and B, each expressed in the form of some orthogonal coordinate system. Now I want to perform A cross B. Again, you would have 9 terms. In dot product, 6 terms would cancel out. Here, unfortunately, only 3 terms cancel out. Why? If you can tell me immediately, then you really understood what I taught you today. For example, let's take a look at the first term. This one cross this one. A1 cross B1. Because the unit vector are the same. Right? Unit vector 1 making a cross product with itself must be 0. Okay? So, when you try to calculate for cross product, remember cross product is asking you to calculate the resulting surface. So the result must be a vector, right? Surface number 1 is pointing in a unit vector 1 direction. Direction is in 1. Then the area must be provided by the length in the second and the third directions. So when this is 1, you will have 2, 3. A2 times B3, right? 2 cross 3 is in 1, but then there's another surface in the opposite direction with these 2 orders permuted, right? So A2 B3 gives you a positive first direction surface, but there must have a negative surface with A3 B. Remember again, this is telling you surfaces are vectors. Okay? So cross products, you have to be very careful in the resulting directions. So the fancy way of writing A cross B is you write down the unit vectors in the first row of a 3 times 3 matrix, and then A1, A2, A3, B1, B2, B3. Right? Again, compared to the past, in the past, you need to calculate the angle between the 2 vectors, and now you don't. You can do direct calculations. So as you can see, I'm going very slow because I really hope by teaching you all these fundamentals, you could really understand the meaning behind all these calculations. And I really hope this is the very last time you learn vector analysis. Okay? Not next year, not next semester, but only this semester. And that's it. Last one. Right? So next Monday, we are going to finish this part 1 set. So there will be set number 2 for vector analysis, and it will be more complicated.